Good to go. Okay, last time we were talking about carbonyl structure and reactivity. We were focusing on what's the impact of this Y group that's attached to the carbonyl carbon. We talked about, is it a good leaving group and is it a good electron donor? Interestingly, one thing that emerged from our discussion is the things that are poorest leaving groups are actually the better electron donors. So you can use your intuition from chapter 2 of 351 where you talked about pKa to identify good leaving groups. Recall, good leaving groups are good because they are stable with negative charges. They are conjugate bases of strong acids, whereas poor leaving groups are conjugate bases of weaker acids. But the flip side generally goes that the best leaving group is the worst electron donor. What makes a good electron donor? Something with high energy electrons, electrons that are not very stable, electrons that are willing to share. So what does this mean for a carbonyl compound? We talked about two different carbonyl compounds. One is the ester, the other is the acid chloride, and we were trying to rank them in reactivity based on the consideration of what's the leaving group / how good of an electron donor is it. So, for example, if you look at the ester, the Y group would be this methoxy group, whereas for the acid chloride, it's just Cl. Cl is a good leaving group, conjugate base of a really strong acid. It's pretty stable on its own. That means its electrons are low in energy, and therefore not particularly good at being electron donors. In contrast, methoxy is a much worse leaving group. Its conjugate acid is an alcohol, which is not very acidic at all, pKa of 16. It has decently high energy electrons, which means it's a good electron donor. Do you see how those are two sides of the same coin? That concept's really, really useful. If you can get it, it'll come in handy a lot of times. So what does this have to do with the electrophilicity of the ester versus the acid chloride? Well, for that, we went and looked at this resonance structure. Woo, that's an eraser, not a pointer. There we go. We showed you the resonance structure where the carbonyl carbon is electron deficient with a positive charge on it, and then showed you how, if the Y group is a good electron donor, those electrons can donate in and stabilize the carbonyl carbon, spreading out the positive charge on it and making it less electrophilic. You can draw this same set of resonance structures for the acid chloride. We won't do it. You could. You just replace methoxy with Cl. Only difference is Cl's not as good of an electron donor, and this sort of arrow shows that electron donation process. So groups that are poor electron donors will not be able to do this as well, will not be able to spread out the positive charge. Therefore, we concluded the acid chloride's more electrophilic and therefore more reactive. Okay, you see the reasoning? Let's try one more comparison, see if you can do it. We're going to compare now the ester, maybe a couple more comparisons, the ester with the amide. Okay, so if you want to go through this process a little bit more slowly, here's the methoxy group. That's what the Y thing is. For the amide, it's NH2 minus. If you need some help ranking their leaving group ability / electron donation ability, you can go to a pKa table, you draw the conjugate acid, and then you look up its pKa, which is 16 for the alcohol, and which is 38 for the amine, which is the better electron donor. Right, it's the NH2 minus group is the better electron donor. It's also the poorer leaving group. Therefore, you would predict that the amide would be less electrophilic, less reactive than the ester. The ester would be more reactive. That has consequences. The workhorses of biology, the things that do the chemistry, the enzymes, the structural proteins that make your muscles are all polyamides, lots of amide bonds. They are not polyesters, and there's a reason for that. It's because the amide is more stable and more robust than the ester, but the reason for that is what we've just described here. Okay? Let's see, one more. Let's go, we're going to keep the ester. This is, I guess, easy. Let's replace the oxygen with the sulfur. This is an ester. This is a thioester. Okay, so ester you already know, we've drawn it above. For the thioester, the Y group, the leaving group, is a negatively charged sulfur attached to an alkyl group. This is called a thiolate. Its conjugate acid is a thiol. If you were to look that up, Me is an abbreviation for a methyl group. You ought to get used to that, sorry. If you look up the pKa for a thiol on the table that I gave you last time, or that would be in your text or on an exam, pKa is 8. So, who has the better leaving group, the thioester or the ester? Thioester does, right? So therefore the thioester, having a better leaving group, also having a poorer electron donor, should be more electrophilic. All right. And that's true. Nature will use, we'll see this when we get to chapter 20, whatever it is, 25, 26 on metabolism. Maybe it's 27, I can't remember anymore. We'll see nature uses thioesters a lot as a more electrophilic molecule than an ester. Nature doesn't use acid chlorides in part because they're too reactive and they're not stable in water. Thioesters are for reasons you can tell looking at the ability of the leaving group, thioesters are less reactive than acid chlorides, so they're more stable in water, but they're more reactive than esters, so they can do chemistry that esters can't do. Okay, one more, questions about that, how to make that judgment call, how to rank carbonyl compounds in reactivity? Okay, we need to deal with aldehydes and ketones, which are sort of a special case. For an aldehyde, the Y group is hydrogen. And for a ketone, the Y group is some alkyl group. We'll make it, say, CH3. Okay? Now, aldehydes and ketones are both very, very reactive. And it doesn't necessarily follow the same trend as all of that pKa business with the leaving groups. Because, first of all, H- is a terrible, terrible, terrible leaving group. Its conjugate acid has a pKa of like 35. But hydrogen is small and there aren't even any lone pairs on it to be electron donors. So H- is both, because of its size and its lack of electrons, it's a terrible leaving group, but it is also a terrible electron donor. Which means that if you look at this resonance structure of the aldehyde, there's nothing that hydrogen can do to spread out the positive charge on the carbonyl carbon. All right, so even though aldehydes lack a good leaving group, they are still extremely electrophilic. And this actually plays a role in biology a lot. Aldehydes are intermediates in a lot of biological reactions, but it explains why nature and humans want to control glucose levels in your blood so carefully. Glucose is an aldehyde. Aldehydes are very reactive, and there are things that glucose can do, undesired chemistry that glucose can do if you don't control the level of glucose in your blood. Yeah?
Quick question, when we're talking, like you said, it's very electrophilic, for the other examples with like the amide and the other stuff, when when we say electrophilic, are we referring to the central carbon, or are we referring to whatever that group is, like that nitrogen?
Right, good. When we say electrophilic, we're referring to the carbonyl carbon. Yep. How likely is a nucleophile to attack the carbonyl carbon? Yeah, not the other group. Yep. So in all of this, we're looking at the impact of whatever that Y group is on how electrophilic the carbonyl carbon is. And the answer for the aldehyde, because it's not a great leaving group, but it's also not a great electron donor, is that it's still very electrophilic. Okay, other questions? So let's compare the aldehyde to the ketone. Here, again, for the Y group for the ketone is some kind of alkyl group. So if you were to draw what that Y group is, it's CH3 minus. Again, that is a terrible leaving group. The conjugate acid of CH3 minus is methane, which has a pK of like 50, meaning never in the history of the universe has methane lost a proton to water, is what that pKa means. Okay, you might expect ketones to be in a situation similar to aldehydes where, okay, it's not a great leaving group, but it's also, we need to examine how good the methyl group is at donating electron density. Looking at this resonance structure, so let's put a question mark by what kind of electron donor the methyl group can be. If we draw the resonance structure where there's a positive charge on the carbonyl carbon and then ask ourselves, how can that methyl group affect the positive charge? There's no lone pairs on the methyl group, so we can't do what we did with the ester where we draw a little arrow and make a pi bond, right? You can't do that here. But it turns out there is an effect of having the methyl group there. There are two ways to understand this. One of them is simple, but high-level quantum mechanical calculations are casting doubt onto whether that simple explanation is true. The other way is more complicated but more robust. I'm not sure which one to tell you guys, because the more complicated one is going to confuse you and make you angry. But the simple one will work in the short term, but then then at some point in the future, you're going to read a headline on Google like I did this week of alkyl groups are not exactly electron donors. And you'll be, what the heck, Dr. Price? You knew this and didn't tell me. So what are we going to do? We're going to go for it. I'll give you the simple explanation, which if you want to, simple oversimplification, which if you want to memorize and go with, that's fine. And then I'll tell you the more complicated one, but not at a super deep level. Okay, so the question is the alkyl group an electron donor? Two possible explanations. The answer is yes, but there's two possible reasons. The first is that in general, sp2 carbons, like the carbonyl carbon, are more electronegative because of their higher S character than are sp3 carbons, right? An sp3 carbon is only 25% S, and sp2 carbon is 33% S. More S character an atom has, the more its electrons penetrate to the nucleus, the lower in energy they are because they're held closer to the nucleus. That's an argument you probably learned in general chemistry and 351. So you would expect there to be, you would expect an alkyl group to be an inductive electron donor. That is, the sp2 carbon can suck electron density through the sigma bond away from the sp3 carbon simply by holding the electrons a little tighter, okay? That difference in electronegativity is not so great for the aldehyde, not as big for the aldehyde as it is for the ketone. So you would predict that the ketone methyl group is donating, that's a little bond dipole, donating electron density through the sigma bonds towards the carbonyl carbon. That's not happening in the aldehyde. You'd predict that effect would tend to decrease how positively charged the carbonyl carbon is, making the ketone a little bit less electrophilic than the aldehyde. And that's generally true. The ketone is a little, not hugely, but a little less electrophilic than the aldehyde. The second explanation is more complicated, but it's actually useful in understanding a ton of things. Depending on the semester, I sometimes decide not to talk about it, but I think we're just going to go for it. So the second explanation is something called, are you ready? Hyperconjugation. It's like conjugation, but it's hyper. No, it's hyperconjugation involves in the same molecule overlap of an adjacent filled orbitals. Sorry, I need to just make that adjacent later. Overlap of, oh, there went the part of the P, there we go. Overlap of a filled orbital with an adjacent empty orbital. So hyperconjugation is in the same molecule, overlap of a filled orbital with an adjacent empty orbital. And we'll talk about this multiple times. We're just going to introduce it today. The idea is the consequences of hyperconjugation is we spread out electrons in the filled orbital towards the empty orbital, and electron delocalization is stabilizing. Well, let's look at the structure of the ketone. What filled orbitals are available on the methyl group to spread out adjacent to the pi star in the carbonyl? What are the only filled orbitals on the methyl group? CH sigma bonds, right? So what hyperconjugation is here in this molecule, and I can draw you an example of it, but it may be enough just to think about it conceptually. In the case of the ketone, it is that a filled sigma CH pair of electrons, one of the electrons from one of these CH bonds, spreads out a little, not completely, but a little bit of partial delocalization into the adjacent carbon-oxygen pi star, which I told you was mostly on the carbonyl carbon last time, right? So we can draw this in a couple of ways, but maybe the simplest way is like this. So let's draw a ketone. Here is the carbonyl carbon. Here is the pi star, mostly on the carbonyl carbon, a little bit on the carbonyl oxygen. We'll use color to signify wave function sign. And we'll put a node here with a dotted gray line in between the two nuclei. Below the plane of the page, we've got another set of lobes that you can't quite see. You just get a little bit of a hint of. Then on the adjacent atom, we've got where the ketone is. Let's imagine we have a CH bond this is going to be sort of dumb to draw. No, we can do it. Sticking out towards us and sticking out away from us. Let's just consider the CH bond that's sticking out towards us. And let's actually draw what a CH bond looks like, a filled CH bond. We showed you this mostly last time. It would look like an sp2 orbital or sp3 orbital on the carbon, overlapping with and extending towards a 1s orbital on the hydrogen. So that's what a carbon-hydrogen sigma bonding orbital looks like. And this is the carbon-oxygen pi star. Recall that the carbon-oxygen pi star is empty. Recall that the carbon-hydrogen sigma is filled. And let's just choose orange here and pink here. There's a node at the nucleus for a sigma bonding orbital. So what we're saying, and just to emphasize that it's filled, I'm going to draw 2 electrons here. What we're saying is that, and you have to envision, this is a terrible drawing. We can draw it from the side, but I think this is good enough. Might make it worse, actually, to draw another picture. imagine the carbon-hydrogen bond coming out at you towards the page. It's basically lined up with, side by side, adjacent to the pi star. Can you envision in your mind that they're side by side? Okay. Some of you are thinking no. Fine. So you're familiar with the Newman projection. We're going to put your evil Anakin Sith eyes in the plane of the page, and we're going to look at that molecule. So here's the carbonyl carbon from that view. To the right is the methyl group. Here's the proton we were talking about. And then here's the R group in the back. You can't quite see it, is the oxygen. And I'm just going to draw the part of the pi star on the carbonyl carbon that you can see. And then here is the sigma bonding orbital on the adjacent CH bond. Two different views of the same thing. This view on the bottom, we can't see the carbonyl oxygen in the back. So I'm going to draw a circle around this carbon, so it's sort of like a Newman projection, so you know where that oxygen is. This is the empty carbon oxygen pi star. This is the filled carbon hydrogen sigma bonding orbital. And the idea is that when a filled orbital in an organic molecule lines up with an adjacent empty orbital, there's a stabilizing effect. It has more consequences than this, but we'll just talk about one today. The electrons in the bonding orbital spread out a little bit into the antibonding orbital. I am saying a little bit on purpose because, as you know, if you fully fill an antibonding orbital, then the bond breaks. This effect isn't that strong. It's not fully like these electrons are hopping completely into the antibonding orbital. They're not. They're perfectly happy between the carbon and the hydrogen. But they spread out a little bit, and that's a stabilizing effect. It's small, but it's important. This is one of the ways that an alkyl group is an electron donor, because you could imagine if these electrons, and I've struggled over the years to figure out how to show this, so we're just going to show them spreading out a little bit. That's terrible, isn't it? That didn't do anything for us. Let's just erase it. We'll try something again next year. They spread out a little bit. Okay, not completely, but the effect will be that they're going to spend a little bit of time towards the carbonyl carbon. That's going to help lower the partial positive charge on the carbonyl carbon and make it less electrophilic. Okay, got that? That's hyperconjugation, and we can talk about why it's called that, but that's good enough for now. Now, just one future predictive thing that we're going to get to, probably not for another month and a half. You might predict that if the electrons in this CH bond are spreading out a little bit towards the pi star, they might be holding on to the proton a little less tightly. You might predict that this proton that's adjacent to the carbonyl carbon is more acidic than you would expect. And you would be right. That's kind of some cool reactivity we're going to get to another time, but not today. Okay, questions so far? So if you hate, go ahead. Yeah, you can think of the electrons in the CH bond moving lower in energy. That makes it more stable, less reactive. That makes the overall molecule less reactive. Yep. The effect of hyperconjugation is to spread out the positive charge on the carbonyl carbon, making it less of a place to attack. So ketones are less reactive than aldehydes. Okay, others? All right, so now we need to talk about reactivity patterns, two different things that can happen to carbonyl compounds. We've dealt with one of them so far, and that is nucleophilic attack. So that's one possible theme. And there, again, you would expect the nucleophile to attack the pi star at the carbonyl carbon, because that's where most of it is, and that's where there's a positive charge in one of the resonance structures. attack at the carbonyl carbon should break the pi bond, giving you this intermediate, which we have called a tetrahedral intermediate. There's another word for this nucleophilic attack. In effect, this is an addition reaction. An addition reaction is one where we add something to the molecule. What gets added? The nucleophile. Okay? Now, we've called this molecule a tetrahedral intermediate because it used to be sp2 hybridized. Now it's sp3 hybridized. The fate of the tetrahedral intermediate is going to depend on the identity of the nucleophile and the Y group, and also on their reactivity relative to a negatively charged oxygen. Why are we even talking about this? Well, let's imagine something else that can happen to the tetrahedral intermediate, and that is, well, let's see. How do we want to do this? That's fine. So we're classifying mechanistic things that carbonyl compounds can do. The second is an elimination reaction. So keep in your mind this tetrahedral intermediate structure, and keep in mind that we have asked before about the Y group. Is it a good leaving group? We're going to ask the same question about the nucleophile. Is it a good leaving group? But before we answer those questions, I want to just connect what we're about to do today with something you saw last in 351 about elimination reactions. The classic elimination reaction was you have a leaving group here, say Br, on what I'm going to call the alpha carbon, and then on the carbon adjacent to it, the beta carbon, you had a hydrogen. And you've done chemistry before where a base removes the beta proton at the same time as electrons kick down to form a pi bond at the same time as the leaving group left, right? That was an E2 reaction. Does that look familiar? Or you're like, oh, darn it, I knew I should have remembered something from when I took 351 before my mission. Some of you are in that situation out there. I feel you. It's going to come back. Don't worry. Okay, that's an E2 reaction, an elimination reaction. Now, the other thing you learned about in 351 was another style of elimination reaction where actually we have to modify the molecule just a little bit, but there we go. There were cases in which it was, got the alphas and the betas wrong, didn't I? This is the alpha carbon, this is the beta carbon. You saw cases where actually the leaving group would just leave on its own first if you didn't have a particularly good base, and you would get a carbocationic intermediate with a positive charge on the alpha carbon, and then usually a very weak base would come and remove the proton. We called that an E1 reaction. Does that sound vaguely familiar? Okay. One of the things you didn't learn, or maybe learned, but or maybe didn't, is there's another version of an elimination reaction that's actually sort of the conjugate base version of E1. It's called E1CB. We'll see examples of this reaction this semester. Notice how in the E1 reaction, the leaving group leaves first and then the base removes the proton. In E1CB, you start out with the same type of situation, proton on a beta carbon. Nope, getting it wrong again. Proton on a beta carbon, leaving group on an alpha carbon. But in an E1CB reaction, and sometimes the structures will be different, I'm just showing you how the mechanism is different. The base removes a proton first to give you a negative charge on the beta carbon, and that's the intermediate you get first. And then, and only then, oops, B stands for beta, not base. I'm really struggling today. Let's make the tail there, beta, alpha, got it? Then the electrons adjacent to the beta carbon kick down and the leaving group leaves. Okay? What was that? I didn't see what happened. Oh, skateboard, there it went. The wheel's turning. I think it thinks it's driving somewhere. Oh well. Do you know, stupid keys, we had got a, 2024 was a terrible year for vehicles at the Price family. One of our vans sort of died. It threw a rod because I didn't change the oil enough. Yes, friends, I am 45 years old and I just did that. So we got a new vehicle and the stupid key fob, like I can't even put on my shoes. I maybe need to lose a few pounds because I can't even put on my shoes without my gut pressing the alarm button on the Kia remote. So I'm there in the morning, leaning over, and suddenly, and it's very frustrating. So I assume that's happening. No, the wheel stopped. Okay, good. Well, anyway, that's a non-chemistry aside. I want you to look at the similarities between the intermediate in this E1CB reaction, where you have a negative charge, beta, to the leaving group. And I want you to compare that to this tetrahedral intermediate. And we've dealt with the question, we've asked, is it a good leaving group or not? So again, think about the similarities between this intermediate, and the tetrahedral intermediate, and the E1CB intermediate. If you can't see it, maybe tilt your head. Let me help you just a little bit. I'm not going to come out there and make you tilt your heads. This is the alpha, this is what we'll call the carbon that's alpha to the leaving group. And this is now beta to the leaving group. Do you see how, as with the E1CB reaction, you got a negatively charged group, beta, to something that could be a leaving group? When you're in that situation, an elimination reaction can happen. Effectively, what happens is lone pairs on the oxygen dump themselves into the sigma star orbital associated with the carbon leaving group bond, thereby breaking the bond, and the leaving group leaves. So that's one thing that can happen to tetrahedral intermediates. So you got to pay attention to, is the Y group a good leaving group? Okay, if the Y group is a good leaving group, you can expect an elimination reaction to occur in which the nucleophile replaces what was originally the Y group. Okay? So, this is why I told you we were going to be asking, is Y a good leaving group? Is the nucleophile a good leaving group? Now, do you remember when we started talking about good leaving groups, I said I wanted you to put a pin in the idea relative to what? Is it a good leaving group relative to something? Here is the what that I want you to be thinking about. The question we're going to be asking is Y a good enough leaving group relative to what I'm going to call the kicker offer, which will be this negatively charged oxygen, what used to be the carbonyl oxygen. The kicker offer is a negatively charged oxygen. And if you look, before the elimination reaction, the negative charge is on the oxygen. After the elimination reaction, the negative charge is on the Y group. Okay? So asking, is the Y group a good enough leaving group relative to the kicker offer, is basically asking, what is the equilibrium constant for that reaction? Is it reasonable for the negatively charged oxygen to kick off the negatively charged Y group? And the answer is, depends whether the leaving group's better or worse than that kicker offer group. Let me illustrate that with an example, okay? Let's just imagine, for the time being, that we're not going to say anything yet about what the nucleophile is, but let's suppose the leaving group was Cl-. let's draw the product that would happen if Cl minus were kicked off by the kicker offer. Here was your nucleophile in purple, okay? And we're basically asking, if we're asking about this reaction, we want to know, is this reaction reasonable? Would it move forward? Basically, we're asking, which is more stable? Having a negative charge on the oxygen or having a negative charge on the Cl? You can figure that out based on a pKa table, right? You're basically asking, is Cl minus more stable than OR minus? And if you haven't got that down, look up the pKa's of their conjugate acids. HCl, what's the conjugate acid of OR minus? It's just an alcohol, pKa 16 versus pKa minus 7. Clearly, Cl minus is more stable. Therefore, it's favorable for the leaving group to leave, right? Somebody always, so you're gonna wanna go through that a little bit slowly, make sure it makes sense. People get confused, what am I comparing to what? You're comparing the group that you're thinking about getting kicked off and what it is once it's left to the stability of a negatively charged oxygen. Okay? Is a negatively charged oxygen a good enough kicker offer to kick off the leaving group? Well, sure, if the leaving group is more stable than a negatively charged oxygen. Okay? How about this? What if the leaving group were another negatively charged oxygen? So again, here's your nucleophile, here's your kicker offer, here's your prospective leaving group, here's what things look like after the reaction happened, here's the leaving group having left. What do you predict? Is a negatively charged oxygen a good enough kicker offer to kick off another negatively charged oxygen? Well, you don't know what to say because you're afraid to commit, right? You think it maybe sounds reasonable because they're about the same stability, but you're not sure whether that's good enough to answer a multiple choice question, yes or no. That's fine. That level of discomfort is actually perfect because what you would say is this reaction here is probably not as favorable in the forward direction as the one where the chloride gets kicked off. I would say this equilibrium constant would be much greater than 1. It would be very favorable for Cl minus to get kicked off. Probably less favorable for OR minus to get kicked off. You might expect that equilibrium constant to be closer to 1. In fact, you might expect this step to be reversible. Right? Meaning, sure, the negatively charged oxygen can kick off another negatively charged oxygen, but the OMe minus that we make is not much more stable than the negatively charged tetrahedral intermediate we had, so probably it's pretty reasonable for the OMe minus to come back and attack the pi star of this and go back to that tetrahedral intermediate. We're going to see reactions that are reversible like this all the time, and knowing whether a reaction's reversible or not is simply an issue of comparing the stability of the leaving group once it's left versus the stability of the intermediate that does the kicking off. Okay? That's sort of following along? Okay. I want to talk briefly about this nucleophilic attack step. And sometimes we will want to know how reasonable is it for this nucleophile to do the, go ahead.
Just about that last one, are both relative, is it reactive? Or, and it's like going back between both, or is it not realistic?
So what I would say is this is definitely a reasonable step. This is a totally reasonable step for these electrons on the negatively charged oxygen to kick off a negatively charged oxygen. I would say comparing these two reactions, this one's very favorable in the forward direction. This one is irreversible. Maybe let me give you an example where the leaving group just flat out can't leave. So that one's easy. What if your tetrahedral intermediate looks like this? Here's your nucleophile, but what if the Y group is a hydrogen? Oops, that's not the kicker offer. Here's the nucleophile, and we're basically asking the question, could the negatively charged oxygen kick off H minus as a leaving group? And the answer is not without a whole lot of other help. Biology can actually do this. But first, to understand the beauty of biology, you have to understand how terribly unreasonable this is. H minus is a terrible leaving group. Its conjugate acid has a pKa of 35. Remember, the thing you're comparing is the stability of the leaving group having left and the negatively charged oxygen, which has a conjugate acid whose pKa is 16. That's we're doing the math and I'm struggling, a 19 order of magnitude difference. So again, never in the history of the universe would you expect negatively charged oxygen to kick off a hydride and have the hydride just go floating off in space by itself. Okay, so that's a heck no. In terms of reasonable stability, not in terms of reasonableness. This is not reasonable. You would not predict that this would happen. You would predict that this would be completely unfavorable. Now, preview for the course. Have you ever heard of NAD plus and NADH? Nicotinamide. It's actually one of the B vitamins. You need it. And one of the reasons you need to do it is NAD plus acts as the thing that catches the hydride when it pops off and captures it so that it doesn't have to be such a terrible leaving group on its own. Okay? So we'll see reactions where H minus can be a good leaving group, but only when NAD plus or something like it is there to catch the hydride. So 3 different reactions. Excellent leaving group relative to a negatively charged oxygen. Okay leaving group relative to a negatively charged oxygen. Terrible, horrible, no good, very bad leaving group relative to a negatively charged oxygen. So let's think about what that would do to reactions. Because if we start to stitch all of this together, we can come up with 2 basic reactivity patterns for carbonyl compounds. One, and I need to come back to something with the nucleophile attacking. It's a similar set of concerns, but maybe we'll do that later. In one case, we have what's called nucleophilic addition reactions to carbonyl compounds. And this happens basically when Y is a terrible leaving group. Nucleophilic addition to carbonyl compounds. So examples of times where Y could be a terrible leaving group might be where Y is H minus or CH3 minus, that is aldehydes and ketones. There are other examples of this. Let me just give you one, okay? And let's be still general about what the nucleophile is. Here's your Y group. Here's your nucleophile. Nucleophile attacks, oops, I want not the highlighter, attacks the pi star, breaking the pi bond to get this tetrahedral intermediate. Then you ask the question, what's next? Is Y minus, actually, which is now just a hydrogen, is that a good leaving group relative to the negatively charged oxygen? And the answer is no. So therefore, you're sort of stuck. The leaving group can't leave. You can't kick it off. And so this tetrahedral intermediate isn't really a tetrahedral intermediate anymore. It's more of a tetrahedral product. And there we stay. Now, normally when we do reactions in the lab, and we want to store stuff on a shelf, it's most convenient not to deal with the negatively charged oxygen and its counterion. It's most convenient to do something that I will call aqueous workup. You will learn what this is if you take the 353 lab. Basically, you end up taking your organic reaction mixture and dumping water on it. Organic and water don't mix, but the water protonates the negatively charged stuff. And then you're able to isolate the neutral organic molecule. There's more to say about that, but you don't really need more at this stage. Basically, we add water to quench the negative charge on the negatively charged oxygen, and we end up with this product, which formally is an addition product. The nucleophile got added to the molecule, and then a hydrogen from water got added to the molecule. Relative to where we started, with a pi bond between carbon and oxygen, we added nucleophile and then hydrogen on the oxygen. This is called an addition product. Nucleophilic addition to carbonyls, and sometimes this is called a 1,2 addition product. In part because the nucleophile and the hydrogen that get added are on adjacent atoms. So sometimes you'll hear people call this not a lot, but sometimes you'll hear people call this a 1,2 addition reaction. Okay, that's reactivity pattern number 1. Reactivity pattern number 2 for carbonyls is what I'm going to call nucleophilic acyl substitution. And this is when Y is a decent leaving group. And I'm going to say good enough. By that, I mean relative to a negatively charged oxygen. Okay? So let's do an example of that. Let's just use Cl minus. Nucleophile attacks. Because we've only got a minute left, I'm not going to highlight in color, though I'm really tempted to. We can do that later. At the end of the semester, you can comment on how much class time was wasted on pretty colors. Cl is a good enough leaving group relative to a negatively charged oxygen, so Cl leaves, and the nucleophile replaces where the Cl was. Purple is now where yellow was, and yellow is now where purple was. And the reason this can happen is because yellow was a good leaving group relative to pink. That's a substitution reaction. With that, we have summarized all of the chemistry you're going to do in chapters 13, 14, and 16. The last thing we need to do at the beginning on Monday, before we get specific, is to talk about this first step, which is nucleophilic attack. There's a little bit more to do there. All right, have a good weekend. I will see you next time.